One important concept that we still have to talk about here in the gas laws chapter is the Dalton's law of partial pressure. And the main idea is that most gases that we come in contact with are mixtures. And the Dalton's law tells us that the total pressure of the gas is equal to the sum of all of those gases. So the idea is, depending on how much gas is present of each type, is going to be how much pressure is exerted by that particular gas. So for example, if we think about the atmosphere, the air that we're breathing right now, it's about 78% nitrogen. And so the idea is we think of that as being, okay, the total pressure is 1 atmosphere, and 78% of that is nitrogen, and therefore the partial pressure of nitrogen is 0.78. So it depends on how much is present. And so what we normally would say is that essentially taking the total pressure, you can find the total pressure by taking the sum of the partial pressures. Okay, and all components follow the ideal gas law. So the main idea there is that you can find the pressure if you just know the number of moles. And as it turns out, we can use something called mole fraction to help us find partial pressures. And so if we take the total number of moles and divide it, take the moles of one particular gas and divide it by the total number of moles, that will give us something referred to as the mole fraction. What fraction of the total sample is this particular gas? And as it turns out, because we consider volume and temperature to remain constant, that we can apply that to pressure. Okay, and so if we can find mole fraction, as it turns out, we can find the pressure of the particular gas. And the way that we do that, looking at an example here, if we have a mixture of gases and we know how many moles of each gas we have, as well as the total pressure, we can calculate partial pressures in mole fractions. As it turns out, the easiest thing to do is, okay, so here is this equation. And so the first thing, mole fraction is much easier than partial pressure at this point. So we can find the total moles of gas by just adding the 3 gases, or the moles of the 3 components present. We can then find the mole fraction by taking, so for instance, for CH4, taking the number of moles of CH4, dividing that by the total number of moles, and that gives us a mole fraction. That is a unitless number because the mole unit cancels. And so again, it is just a fraction. You can do that for the other 2 gases, and that calculation is shown here. So that's mole fraction, but it hasn't necessarily gotten us to partial pressure. Well, if we look at this expression right here, we can see that the partial pressure of a gas divided by the total pressure of that gas is equal to the mole fraction of that gas. We now know the mole fractions, and we know the total pressure because that's given to us here. So what we can do, we can rearrange this expression by multiplying both sides by the total pressure. That means the partial pressure is going to be equal to the total pressure times the mole fraction. What fraction of that mixture is a particular gas? And now we have all of the information that we need. We have the total pressure, which is 1.5 atmospheres, 0.365, and so this works out to be 0.548 atmospheres. You can do that for the other 2 gases, and as it turns out, if you add up all 3 of these values here, if you add all 3 of these values, it adds up to 1.5 atmospheres. And that makes sense because the total pressure has to be equal to whatever the total pressure was told to us in the problem. And so this is one application of partial pressures, a real important application of partial pressures, and one in which I will be working a problem using an iPad video instead of PowerPoint like this, is collecting gas over water. So the idea is, if we do a reaction and the gas is what we care about, okay, the gas is the product that we care about, sometimes it's difficult to actually collect that gas. And so one way to do it is to have a reaction going and make sure that whatever gas products are being given off are pushed through water and into a bottle, which is then going to displace the water. So as the air or the gas fills this portion of the bottle, the liquid is being pushed out. Okay, and so we can then measure the volume of that gas. Now, the issue there is that when we're collecting gas over water, yes, we are. So in this case, we're collecting oxygen. So yes, oxygen is present in this sample. However, because we're collecting it over water, there's also some water vapor, okay, some humidity that is present there. So the total pressure, as it turns out, is equal to the pressure of the oxygen plus the pressure of the water. And what we have to do to be able to solve for the amount of oxygen that is present is we have to subtract what is referred to as the vapor pressure of water. And the vapor pressure of water is something that has been measured a lot. And so, as it turns out, as we increase the temperature of water, the vapor pressure goes up. And so there are tables like this. There's also a table in your book that show this water vapor pressure at particular temperatures. And so we need to use that pressure and subtract it out from the total pressure in order to get the pressure of the gas that is being generated. And again, this is something that I'm going to work a problem on to show you how it works. Essentially, we're just correcting that total pressure. We're subtracting out that water so that we can only deal with the product of the chemical reaction and not have to worry about the actual water that is present. And so again, there's going to be an example video that is going to accompany this this topical video so that you can see exactly how we can apply Dalton's law to collecting gas over water.